Hello and welcome back, everyone. Today we're going to be talking about the definite integral and why exactly this gives us the area under a curve. Now, you can come back to this video after we've spoken a bit more in class about integration because we're just getting started on this topic. This is more Chapter 8 material for those of you just about to start Chapter 7 for methods. But we're going to be jumping ahead a little bit and just kind of looking at exactly what the integral is and what its connection to the area under the curve is. So before we get into that, there's a couple of definitions that I want to talk about. The first couple here, or the first one, should be nothing new to you. So this is the definition of the derivative. So we say that the derivative, which is f dash of x or dy dx, these all mean the same thing. This refers to a small change in y over a small change in x. It's like a fraction, right? Like the change in y, delta y, you would say. The d is for delta or change in. So we have a change in the y value divided by a change in the x value, which is the same thing as saying rise over run, for 2 points that are really close to each other on the curve. So this is the instantaneous rate of change, or the gradient between 2 points. We call these 2 points f of x plus h and f of x. And h, in this case, is a number that is really, really small, but not quite zero. So we say that the limit as h goes to 0 is equal to this thing here, which is called the difference quotient. Quotient just means something that involves division. So this difference quotient, as h goes to 0, is called the derivative. The fundamental theorem of calculus states that the relationship between the integral and the derivative is that these two things are inverse operations to one another. So the fundamental theorem of calculus is written in these two ways here, but what it essentially boils down to is if I have some function, if I call that one, I don't know, let's call it capital F to distinguish, right? So if I take capital F and I take the derivative of capital F, so if I derive it, then I'm going to get something maybe f of x, which is equal to capital F dash x. And if I was to take that function, fx, and integrate it, so the process of going this way, it's called integration, then I'm going to get back f of x. So if we think about the derivative as finding the gradient of a particular function, you can think about integration as being like, okay, if we know that this function is the gradient, how can we work out what the original function could have been? And as we're going to see, there are actually infinitely many ways that this could occur, because there's always going to be this thing called the constant of integration. But we'll talk about that in class. So let's not talk about that now. All I wanted to talk about in this video, because otherwise we'll be going off on a bit of a tangent, no pun intended, is something to do with the fact that inverse integration and derivatives are inverse operations of one another. And the third one here, the squeeze theorem. This one here is something that you have not learnt in class, but it should make sense to you. So the idea is if there is some function g of x, and it is always greater than or equal to f of x, and also always less than or equal to f of x, then f of x and g of x must be the same thing. So you can think about this as it's squeezed in from either side. If I wrote it in a slightly different way, if we have a number a, and we know that a is greater than or equal to something else b, and it's also less than or equal to b, that implies that a must be equal to b. They must be the same thing. And this is just the same idea, just applied to functions. All right, so that's the squeeze theorem. And this final definition here, this is what I'm going to be talking about throughout the video, and we're going to come back to it. So it's the Riemann sum definition of an integral. And it's basically telling us that the integral is equal to the area under the curve. So I'll come back to this definition here, but just to unpack what it's saying, this notation here, the integral from b to a, is basically saying, given some function, like this blue curve here, if I was to choose 2 points that lie on that function, let's say, for example, I take like a and b, and I want to find the integral between these 2 points, well, at this point here, we're going to get out a value of f of a. At this point here, I'm going to get out a value of f of b. What we're trying to find here is the integral between those 2 points. So this would represent, if this blue curve was the gradient, what function would give us that gradient function as its derivative? So in other words, it's the gradient between those 2 points. And specifically what this is, as we're going to see in class, is it is defined as the area under the curve between those two values. So that shaded region there, the claim is equal to the integral from a to b of f of x with respect to x. And lastly, this dx thing at the end here is just saying with respect to x. So take the integral of the function f of x with respect to x. It's telling us that x is the variable in this scenario. So we're going to be proving why is this equal to area? Why is that the case? So to answer this question, let's consider a couple of curves. So we're going to start out by considering this first curve over here. It's just the same curve, just drawn three different ways. And I want us to take, for example, not A and B, but let's just take any one particular value on this curve. So let's say we're interested in this particular value, X. Maybe let's use a different color. Let's maybe use black, I think, for X. So we're interested in X. Let's say X is right here on this minimum here. Okay, so let's just put it in for all three graphs. Now, what I am interested in is the area under the curve. So let's just start by considering this area here from that y-axis there. I mean, we can continue it. It can be everywhere on the function up to that point. That's going to be called our first area, and I'm going to name that area a of x. So the area x is clearly related to this area in some way because if I change the value of x, that's going to change which area is shaded under the curve. So I'm just going to call that particular area a of x. Now let's consider another section of area. I'm going to take that same thing here. We're going to go from x, but this time we're now going to consider a point that's really close to x. So as tends to be the case with calculus, we tend to be taking a point that's infinitely close to the first point we chose. I'm going to call this x plus h. Or we could even call it x plus delta x. Whatever we want to call it, doesn't really matter. So that's telling us that the difference between these 2 points is something that's called h or delta x, which is dx or the change in x. Whatever you want to call it, it doesn't matter. So long as it makes sense to you that this difference between these two values is that delta x or that h value between those 2 points there. And now what we're going to consider is just that area leading up to this point here. So if we consider all of that area there, like we said, that the area is clearly dependent on what input we put in. So this area here, we could just call x plus h, right? The area up to that point. So finally, let's consider a different area. Now, what we're interested in, as is the case with calculus, is we're trying to probably take the limit as h goes to 0. So what we're interested in is the area between these 2 points. So we're interested in this area right here. So this area right here. And what would that area be equal to? Well, that area is simply this one here, a of x plus h, minus a of x. That's going to give us that little wedge. We can even see it over here in the second diagram, the wedge in the middle there. So that wedge is equal to a of x plus h minus a of x. All right. Now, what claims can we make about that area? I'm going to zoom in on that diagram for a minute there. What claims can we make about that area? Well, something that we might notice is if we were to approximate this little section here, we could approximate it as though it was a rectangle, and we could do this in a couple of different ways. For example, in fact, let's draw a fresh diagram for this one over here. Let's draw it over here. There's a couple of different ways that we could look at this. So let's consider that curve. Use blue to keep everything consistent. All right, there it is. So we could consider this by thinking about that first stretch from x to x plus h. So let's say I might want to take a copy of that. See if the program lets me do this. I haven't tried this one before. That may have broken the PDF document. All right, let's maybe not worry about that. So let's say we're trying to find this area here. So we could take, for example, so we can consider this. That's better. Okay. That's better. There we go. All right, so let's consider this rectangle, right? So the rectangle from here to here. I'll just zoom in on that. You'll have a look. So let's consider that rectangle there, that little orange one there. What is the area of that rectangle? Well, that area will be given by, if we think about the area of rectangle is length times width. So we can say that the length of this object here is going to be the height. So the height of this shape is f with an input of x, right? And the width of that shape is h. Okay, so we can say that that area there, and I'll write it down over here, is equal to f of x times h, length times width. Now let's consider another diagram. Maybe we'll use green this time. Okay, now let's say if I was to draw this rectangle with this as the height, then we're going to get a rectangle that would look like this. Okay, and if we took that as the height, well, what would the height be? Well, it would be f of x plus h. So the function with an input of x plus h, and the width is still h, right? So I'm going to write that over here. That's area is f of x plus h times h. And what you should be able to see visually about this diagram over here is that that green area over there is larger than this red area that I drew up here. And also the purple area is smaller than the red area that I drew up there. So we end up with the following inequality. We're going to end up with something that looks like this. We can say that that area is less than or equal to, and this other one is greater than or equal to, a of x plus h minus a of x. That's what we end up with here. And now we can kind of do a couple of tricks to this. So the first thing that I'm going to do is I'm just going to take both all of this sides of this inequality and divide everything by h. So that's just going to just divide everything by h. This should be fine. I'm allowed to do this so long as I apply the same operation to all sides of the inequality. So I'm going to divide this by h. I just end up with f of x. Divide this middle bit by h, so I end up with that fraction there. And if I divide f of x plus h times h divided by h, I just end up with f of x plus h. And now we're going to do what I alluded to this whole time, which is basically take the limit. So we want to know, essentially, as h goes to 0, what happens? And I'm going to have to spill onto the following page to look at this. We're going to get the following things occur. F of x just stays as f of x, doesn't get changed. This one over here, f of x plus h, goes to f of x, right? So as h approaches 0, this just becomes f of x plus 0, that just becomes f of x. This thing in the middle, have a look at what happens to it. We end up with the limit as h goes to 0 of a of x plus h minus a, let's fix that one up. So the limit of a of x plus h minus a of x over h is less than or equal to f of x. So like I said, f of x plus h becomes f of x as h goes to 0. That thing right in the middle there, what is that? Well, that is nothing but the definition of the derivative. That's this very first thing that I wrote up here, the difference definition or the limit definition of the derivative. So what we end up with is that this thing in the middle is in fact the derivative of the area under the curve, ax. This function that I want to figure out. What is this function, a of x? Well, what we've shown here is that whatever that function is, the derivative of that function is always greater than or equal to f of x, and it's also always less than or equal to f of x. And by that thing that I wrote up here, the squeeze theorem, we can now see that, well, that a dash x, it must actually be equal to f of x. Because if it's always greater than f of x, always less than f of x, it must be equal to f of x. So we can say, therefore, by the squeeze theorem, which is this theorem that we've just learnt about here, should be fairly intuitive, but the proof is, like beyond the scope of this course, so we don't have to worry about it. By the squeeze theorem, we can say that f of x must be equal to a dash x. Okay, so where does this leave us? Well, if we can say that the function is equal to the function f is equal to the derivative of a dash x, this implies, by the fundamental theorem of calculus, so I'm going to write that out, by the fundamental theorem of calculus, that implies that the integral of f of x between these particular points, which in this case was just any two particular points on the curve, it doesn't really matter, so any points on the curve, is going to be equal to a of x, because of course the integral of the derivative is the original function. So they cancel each other out. We can see that the integral is equal to the area, and that's kind of what this is all about. So what does that tell us about this formula right here? So what does this formula even say? Well, what it's saying is that if I wanted to find the integral between these two particular points, a and b, one thing that I could do is think about that difference between those 2 points as a whole bunch of rectangles, just like this rectangle here, or just like this tiny little smidgen. And if we approximated that as a whole bunch of rectangles that looked a little bit like these purple and green rectangles down here in the bottom left, if we were to approximate that like that, and if we were to make the number of rectangles infinite, then we're going to get the area under the curve, which, as we can see, is the integral. So what this notation here is telling us is that the integral between a and x of f of x is equal to the limit as n goes to infinity of the following sum. So remember, this notation here means sum. It's the notation where this dx here is the width of each of those rectangles. So if we were to find a whole bunch of rectangles that look like this, each of their widths is going to be equal to delta x, right? And I'm going to be summing a whole bunch of xi. So xi is kind of like the number of ones that we're looking like. In fact, it's written here. So if we think about, for example, xi, this first one here, this one here could be equal to a of, for example, like the first one would be a plus 1 dash. So I think there should be an I here. So this could be equal to a plus delta x, just 1 delta x, or the next one here, this one here would be equal to a plus delta x plus delta x. So it's like the next one along, right? So each of those areas, the x value, which they're going to be defined by, is like the ith xi in this infinitely many series of rectangles here that are defined by their width. So they're all equal to that xi plus or times the times its width, and the function at that point is the f with an input of xi. So for example, the function at this particular point here, that one that I've just drawn, is going to be right here. So it'd be equal to f of xi. So the function with an input of xi. So we can see that the area of that rectangle is going to be equal to its height times its width, or approximately equal. You can see it's not like a perfect estimate. There's always going to be a little bit of space left over, just like we saw over here. That purple rectangle there, it's not quite perfect. It's that little bit of annoying space up the top here, which doesn't quite get captured. But if we make the number of these rectangles infinite, and if we make the space between them really, really small, so approaching 0, we can find that this will exactly be equal to the area under the curve. And that's what this notation is saying. So we say that the delta x is going to be equal to b minus a divided by n. So for example, if this was just, for example, n was equal to 2, then we would say we're just dividing this into 2 parts. And that's not going to be a very good estimate for the area under the curve, is it? So if we think about, we're taking this area here, we just divide it into 2 parts. Well, the first rectangle, maybe we'll do it in the second one over here. So if we wanted to approximate this difference here, the first rectangle, that would be given by this area here, and the second rectangle would look like that. That's not going to be a very good estimation for the area under the curve. What if I split it into, say, 4 rectangles? So we can say, like, first ones look like that. All right, so now we're going to get, this is our first rectangle, that's our second rectangle, that's our third, and that's our fourth. Once again, that is not a particularly good estimate of the area under the curve, but you can imagine if the number of these rectangles becomes infinite, which is to say that the width of those rectangles becomes infinitely small, then we're going to get the area under the curve. And that is what the integral is. So there's a few different ways of looking at the integral, but the overall message here is that essentially what the integral is, it's the area under the curve of a function, and that's why it may be useful. And there's a whole bunch of different contexts in which this will be useful, and we'll be exploring those in class. And there's a whole bunch of different ways that you can find the integral of different functions. But again, I just wanted this little video here just to start things out, just by explaining what the integral is and why is it the area under the curve, because sometimes people get a bit confused about that little detail right at the start. So that hopefully this video was somewhat useful to you. Once again, maybe come back and check this video out once we finish chapter 7, beginning chapter 8. It might make a little bit more sense to you then. But yeah, that's what I wanted to talk about today, and I'll see you guys next class. Have a good one. See you next time.